So this video is going to focus on how do we solve polynomial and rational inequalities. All right, so we're going to do a couple examples with some polynomial inequalities, a couple examples of some rational inequalities here. So let's go through our steps here first for solving polynomial inequalities. So the first thing that we are asked to do is to solve the equation f of x is equal to 0. So essentially, kind of sort of think about like when you solve quadratic equations, one of the, the first thing we want to do in solving quadratic equations typically is to bring everything over to one side of the equation, set it equal to 0 so that you can then solve it by factoring or the quadratic formula or something like that. Think of this as almost the exact same thing. Taking a look at this inequality, we want to turn it into an equation. So essentially, we're going to ignore the fact that it's an equality, and we're going to set it equal to 0. Or at first, what we're going to do is we're going to take our inequality symbol, make it an equal sign, right? And we want it set equal to 0. So we want to go ahead and move anything over to one side of the equation so that it really is set equal to 0 here, right? All terms on one side is equal to 0. So that we can then solve this equation. And if we're solving this equation, this is a quadratic equation, right? And there's many ways to solve a quadratic equation. Now, in my opinion, the easiest way to solve a quadratic equation is by factoring. So I like to factor trinomials using the no fuss property here. So the way that no fuss factoring works is this. I'm going to go ahead and draw my parentheses, set that equal to 0. And first step says to take your first term here, ignoring the exponent, and repeat that twice, 2x and 2x. Step 2, take your first number, multiply it times your last. That's going to give us 2 times the 15, which is 30. So you want factors that are going to multiply to 30, but are going to add or subtract to get your middle term here, which is a 1. Now that's going to be a 5 and a 6, right? 5 times 6 is 30. 6 minus 5 is going to give us that 1 there. So put in the 5, put in the 6. If your last term is negative, you know you're going to have different signs. Whatever sign your middle term is, that sign needs to go with the bigger number of the two. So I'm going to put the plus with the 6 and the minus with the 5. Last step in using no fuss factoring, reduce one or both of your factors. There's nothing in common between a 2 and a 5, so I'm just going to drop down that 2x minus 5. But a 2 and a 6 does have a 2 in common, so I'm going to divide that out. And when I do that, I'm left with an x plus a 3. Now that we have our quadratic equation factored, we go to our zero factor property, which says split your factors up, set them each equal to 0, and solve. So separate your parentheses, set them each equal to 0, and solve. Your solutions here, right, according to our steps here, once we're done solving, your solutions are going to be boundary points. So we're going to talk about that more here in just a little bit. So when we solve this, we're going to add that 5 to the other side, and then we are going to divide by that 2 to get x is 5 halves. And then subtracting that 3 on the other side gives us that x is a negative 3. So what that means, so these are not your solutions here. Keep in mind that this is an inequality, and when it comes to inequalities, your solutions tend to be ranges of numbers, right? From some number to some number, maybe like 3 to infinity, or like 0 to a positive 5, or something like that. All right, so we got a negative 3, and we also got 5 halves, which is just 2.5. All right, these are our boundary points. What we need to do after this point here is we need to test our intervals to see where our shaded region is going to be, where our actual solutions are, right? Are they on the left side here, or in the middle section, or are we shading to the right? Now, I like to use the following rule when I do this. I find the section that has 0 in it. So 0 would be right here in the middle between negative 3 and 5 halves. Plug in a 0 into your original function here. So I'm going to throw this into this inequality, right? And if I throw in a 0 here, so let's see, plug in a 0. And see, does this give me a true inequality here? Well, 0 squared is a 0, and 0 times 2 is 0, so that disappears. And 0 plus 0 is still 0. So I'm left with something that says 0 is greater than 15. Now, 0 is not greater than 15. That is not true. So what that tells me is this middle section is not going to work. Now, rule of thumb when it comes to these, you are either shading the middle section or you're shading the outside sections over here. Since the middle section did not work, that means I am going to shade the outside section's right over here. Which means my solution, always written in interval notation, coming from the left here, is coming from negative infinity up until this negative 3. Union, the 5/2, going to a positive infinity. Now let's move on to our next example here. So we are going to solve the equation f of x is equal to 0. So that means the first thing I'm going to want to do here is plug in an equal sign instead of my inequality symbol. And then I'm going to automatically move everything over to one side of the equation. So I'm going to subtract 4x on each side. I'm going to subtract that 4 on each side so that everything is over on one side of the equation, set equal to 0, so that we can then solve this. Now, if we're solving this equation here, right, so we're solving a polynomial equation by factoring. Now, because I have 4 terms in this problem, having 4 terms is a good sign that you are looking at a factor by grouping problem. Factor by grouping tells us to do this. Chop your problem in half, split it in the middle, right? 2 terms on one side, 2 terms on the other side. Factor out the GCF from each grouping here. So we're going to pretend like this is its own problem. What is the GCF of x cubed plus x squared? Well, they have an x squared in common. And I'm going to factor out x squared. And when I do so, I'm left with x plus 1. I'm going to do the same thing for the back grouping. I'm going to treat this as if it's its own problem and factor out a GCF. Now, if you are factoring out a GCF from the problem and the leading term is negative, keep in mind you do need to factor out that negative with it. Otherwise, we do have a 4 in common here, so our GCF is going to be a minus 4. And when I factor out a negative 4, I am left with, well, an x plus a 1. All right, and that all equals 0. Next step in factor by grouping, notice we do have the same factor inside the parentheses. That is supposed to happen every single time with factor by grouping. But now we have that factor in common. So we're going to factor out x plus 1. All right, and let's see what we're left with when we do that. When we factor out x plus 1 divided out of our problem, x plus 1 is going to cancel here, leaving us with x squared. X plus 1s are going to cancel here, leaving me with that minus 4. Once we have it factored, once you have your sets of parentheses here, split your factors up, set them each equal to 0, and solve. So I'm going to go ahead and write that over here. I have an x plus 1, and I'm going to set that equal to 0. And then I have an x squared minus 4, and I'm going to set that equal to 0. Subtract the 1 on each side over here to get x is a negative 1. Add the 4 on each side. Take the square root of each side so that that square and square root does cancel, and x is equal to a plus or minus 2. Now keep in mind, these are our boundary points. So when we go over here and we look at our line graph, we are looking at a negative 2, a negative 1, and a positive 2 here. Now, when it comes to the shading here, so shading works every other section when it comes to this. So when I'm going to test my intervals here, again, so because we have 3 boundary points, that creates 1, 2, 3, 4 sections here. I'm still going to test the section that has a 0 in it. The section that has a 0 in it is right over here. 0 would be between a negative 1 and a 2. And I'm going to plug 0 into my inequality and see if it's true. Now when I plug that in, I get 0 cubed plus 0 squared. Is that less than or equal to 4 times 0 plus 4? Well, 0 cubed, plus 0 squared is a 0. So is that less than or equal to the right side, which says 4 times 0 is 0. So we just have this 4. So this says 0 is less than or equal to a 4. Well, 0 is less than or equal to a 4, so that is true, which means this section I just tested is true, which means I'm going to shade it. Which means I'm not going to shade the sections on either side of it, right? I'm going to skip the section on the right, I'm going to skip the section on the left, and then I would shade this section right over here. It is every other. So interval notation is going to look like I do have a less than or equal than symbol, so I am going to have brackets here. Otherwise, interval notation coming from the left, this is going to be a negative infinity up into this negative 2 with a bracket because of our symbol. Union, anytime you have a gap, and we're going to pick back up over here at this negative 1 until we get to this 2 here. So that is what our interval notation is going to look like for this problem. Now, the process for solving rational inequalities is just a little bit different here. So we still want to solve the equation f of x is equal to 0. So we're going to take this rational inequality here. We're going to get rid of our inequality symbol and set it equal to 8. Well, this one's set equal to a 2 currently. All right, so we still want to move everything over to one side of the equation. But when it comes to rational inequalities, we want to bring all terms over to one side and into a single fraction. So let's worry first about bringing everything over to one side. So that means I'm going to subtract the 2 on each side, and I'm going to drop down the x plus 1 over x plus 3. And now we said minus a 2. And that's now going to equal 0. Now keep in mind that I can write 2 as a fraction, and that's going to be 2 over 1. Because our steps here say to bring terms to one side and then into a single fraction. I have 2 different fractions here on the left-hand side. We want to get common denominators and combine these into a single fraction. Now, common denominator of 1 and x plus 3, well, common denominator of 1 and anything else is whatever that anything else is. So x plus 3 is our common denominator. So what we actually need to do here is we're going to take this 2 over 1, right? And what we want to do is we want to convert it into a fraction that has x plus 3 as its denominator. So keep in mind the process for doing that. You want to multiply your current fraction by what's going to turn it into the new denominator here. You're going to multiply your current denominator, right? So 1 times what would give you x plus 3? Well, 1 times x plus 3 would give us x plus 3. So we multiply numerator and denominator by x plus 3. Now multiply out the numerator. 2 times x is 2x, plus 2 times 3 is a 6. This is our converted fraction. So back over here in our problem, we're going to drop down to x plus 1 over x plus 3, minus 2 is now equal to 2x plus 6 over x plus 3 is equal to 0. That's what we got when we converted the fraction. Because in order to subtract fractions, we need common denominators. Once we get common denominators, we're going to combine our common denominators and you're going to subtract your numerators. But do keep in mind when you do that subtraction, we have x plus 1 minus 2x plus 6 is what we're doing here. So since we're subtracting, keep in mind this is x plus 1 minus all of this. This minus goes to everything in your second numerator. That means we need to distribute this. So this is really x plus 1 minus a 2x minus the 6. That's what our actual numerator is when we simplify that. So when we combine like terms here, we actually have x minus a 2x, which is a negative x. And then we have 1 minus 6, which is a negative 5. And that is going to equal to 0. Now that is as far as we need to go. Move the 2 over to the other side. Get common denominators to join them into a single fraction. Once you have a single fraction, our steps say set the numerator and denominator equal to 0. So our numerator is a negative x minus 5. We're going to take negative x minus 5, set that equal to 0. Our denominator is an x plus 3. We're going to take that x plus 3, set that equal to 0, and solve these equations. Which means on the left, I'm going to add that 5 to each side to get negative x is equal to a 5. Divide each side by a negative 1, and we get that x is a negative 5. Otherwise, subtract 3 on each side over here to get x is a negative 3. So same rule applies here. Your solutions are boundary points. So back on our line graph then, our solutions were a negative 5 and a negative 3. So go ahead and put a negative 5 and a negative 3. We will be using brackets for interval notation, but we do need to test our intervals to see where we are shading. I'm still going to use the section that has a 0 in it, which is going to be all the way over here on the right-hand side. So plug that in to your original problem, which would be 0 plus 1 over 0 plus 3. Is that greater than or equal to 2? Well, these zeros are insignificant here. That really leaves us with 1/3. Is 1/3 greater than a 2? Now, 1/3 is not greater than a 2, so that means this section did not work. which means we are shading the middle section and then not the ends, right? We're either shading the middle or we're shading the outsides. But since this section didn't work, that means we're shading the middle, which means our interval notation with brackets here is going to be open bracket, -5 to -3. Oh, I'm sorry, close bracket. I almost forgot one tiny little thing here with this specific problem here. Over here at the end, when we take our numerator and set it equal to 0, take our denominator and set it equal to 0, the boundary point that we get for our denominator is always going to have a parentheses with it, because this belongs to the denominator, and we don't want our denominator to actually equal 0. Keep in mind that if you have 0 in your denominator, that is actually undefined. So we don't want it to equal that number, but it could be greater or less than that number. So almost forgot about that here. So when it comes to your denominator solution over here, the -3, the -3 has to have a parentheses because we don't want it to equal -3. So I need to go ahead and switch that here. Always for the denominator. The denominator boundary point should always have a parentheses. The other one, it's going to depend on what your symbol for your problem actually says. But your denominator will always have a parentheses. So let's do that one more time. Let's move the 3 over to the other side, right? And switch our inequality symbol to an equal sign. So this is going to look like x plus 4 over 2x minus 1 minus the 3 we just moved over is equal to 0. That 3 is going to become 3 over 1, which means we do need to get common denominators. Keep in mind, common denominators of 1 and anything else is that anything else. So 2x minus 1 is our common denominator here. So we need to take our 3 and we need to convert that to have a denominator of 2x minus 1. Now, 1 times 2x minus 1 would give us 2x minus 1. So we're going to multiply numerator and denominator by 2x minus 1. Distribute the numerator. 3 times 2x is a 6x. 3 times that minus 1 is a minus 3. So 3 over 1 is actually equal to 6x minus 3 over 2x minus 1. So let's go ahead and plug that in over here. Keep in mind that when we actually subtract this, we're going to join our common denominator together. We're subtracting our numerators, x plus 4 minus the 6x minus 3. So keep in mind we're actually doing x plus 4 minus this 6x minus 3. We do need to distribute that minus to make that x plus 4 minus 6x plus 3 because of that double negative rule. So when we actually combine this together, this is 1x minus 6x, which is a negative 5x, and then 4 plus 3, which is a 7. So once you have your numerator and your denominator here all simplified, you have it into a single fraction, you can take your numerator, set it equal to 0, take your denominator, set it equal to 0, and solve to get your boundary points. Subtract the 7 on each side here, which is going to give us this negative 5x is equal to negative 7. Divide by that negative 5 to get x is a 7/5. On our other equation here, add the 1 to the other side to get 2x is equal to a 1. And divide each side by 2 to get x is a 1/2. When we do our line graph here, so let's see, our 1/2 is going to be over here. And our 7/2 is going to be over here. It is greater than a 1/2. Right? And we are going to test our intervals. Now with this one, 0 is all the way over here on the left-hand side. So I'm going to plug in 0 to our original equation, which is going to be 0 plus 4 over 2 times 0 minus 1. Is that less than or equal to a 3? Well, 0 plus 4 is just a 4 up top. 2 times 0 disappears, so this is just a negative 1 down bottom. So that's really just a negative 4. Is that less than or equal to 3? Now, negative 4 is definitely less than or equal to 3. So that means the section over here where we tested 0 is true. All right, we plugged in 0. It worked, so we shade that area. And keep in mind, the shading is every other, so we do not shade the middle. but we do shade the right side over here. Also, before we write our interval notation, keep in mind the boundary point for our denominator. So our denominator was the 2x minus 1, which is this one here. We got x is equal to 1/2. So 1/2 absolutely has to have a parentheses for the interval notation. Otherwise, do note we have that less than or equal than symbol, so the other one should be a bracket here. So our interval notation coming from the left should look like negative infinity to that 1/2 parentheses, union anytime you have a break, and then we have a bracket over here with that 7/5 to infinity.